Hi everyone. In one of the previous lectures, which was actually a discussion session with undergraduate and some graduate students, I had discussed how to design an RC filter. So that RC filter was used to filter out noise in a reference circuit. Now, while discussing that, I had showed in one of the slides a current mirror that looked like this. So I had a current mirror circuit, and then I had an RC filter inserted in the current mirror circuit. Now, I received one of the comments. I'm not sure where, whether it's on LinkedIn or on YouTube. I don't remember now, but one of the comments that I'd received or mails I'd received is that why is this capacitor connected between the gate and supply? I mean, it's just a filter. So if you want to add a capacitor, why not just add the capacitor here to ground? Is there any difference? So in this lecture, I'll try to answer that very simple question. Yes, there is a big difference between the two configurations, and I'll try and answer what is the difference in this lecture. Okay, so this capacitor arrangement where you connect between gate to ground is what we call a ground referred capacitor. The other arrangement where we were connecting the capacitor between gate and supply is what we call a supply referred capacitance. Remember, one terminal is always at a fixed potential. Whether it's ground or supply, it's always at a fixed potential. Okay, so this arrangement where it's connected to the supply is what we call a supply referred capacitor. Now, mind you, the capacitance is same. I mean, as far as the AC signal is concerned, because this is AC ground, this node is AC ground, and if I connect the capacitor to ground as well, this is DC ground and it's also an AC ground. So for an AC analysis, it's the same. But there is one fundamental difference between these two arrangements, and why do we do that is what I'll try and explain in this lecture. Now, before we go to answer that question, I'll just quickly brush up the basics of current mirrors. Now, let's say we have an arrangement like this. So a current mirror is a device, is a circuit where you have typically two devices. So one device is what we call the reference device or the reference generating device, which is typically a diode connected PMOS or an NMOS device. And then you have a mirroring device whose dimensions will typically be a multiple of the reference device. Okay, in this case, it is n times the reference device. And the output current is given by, because the VGS of both these devices are exactly the same, the output current is given by the ratio of the W wells of these two MOSFETs. In this case, it is N times the input current, which is IF. Now, the operation of current mirror, I've already discussed this in one of my previous lectures. I think it's in my introductory course on microelectronic circuits, which I offered at BITS, and I've uploaded those videos here on my channel as well, where we discuss the current mirrors at a very basic level. You can go through that. So I said we'll just try to look at current mirror, the operation of current mirror. The act of current mirroring can be seen as a two-step process. The first step is that the reference current first creates a reference voltage. It generates a reference voltage. And you apply this reference voltage to a mirroring device. The mirroring device then does the inverse operation, which is it generates a current in response to this voltage. So this reference device converts current to voltage, and the mirroring device converts the voltage back to current, right? So if you see here, the reference current creates a VGS across this, a DC quiescent VGS, and you apply the same VGS to this MOSFET, you get a current which is the ratio of the W wells between the two devices times the input current. So that's the operation. And I've also used the word which is something, again, the old school textbooks used to use that word, which is such circuits are called translinear circuits. What do I mean by translinear? We know that MOSFETs are nonlinear devices, right? So if I pass a current IREF through a MOSFET, the gate to source voltage that it's generating is a nonlinear function of the current. Okay, or we know that the current is a nonlinear function of the gate to source voltage. Now first, the current to voltage generation is a nonlinear operation. But when you apply the same voltage to a mirroring device, it does an inverse nonlinear operation, and the output current then happens to be a scaled version of the input current. So that's why, even though these two devices are nonlinear, the output DC current and the input current are linearly related. So such systems, we used to say them as translinear circuits or externally linear and internally nonlinear systems. Internally, these two devices are nonlinear, but at the end, when you look at the output currents and compare them, the relationship is linear. So if I draw the input current, which is Iref, versus the output current, you can see there is a linear relationship between the two. Okay, and so such circuits are called translinear circuits. I've already discussed this in that introductory lecture. Now, one thing to keep in mind is that this current mirror is a non-discriminative current mirror, meaning it will just multiply whatever be the reference current by a factor n. So if the reference current has some noise In, the noise also gets multiplied by the same value. So therefore, the noise power at the output, INO square, is n square times In square. In is the input reference noise. Now here, I've assumed that there is no noise in the current mirror. So meaning that neither the reference nor the mirroring device noise is so high. Meaning the reference current noise here is the most dominant source of noise. That's submerging or dwarfing all other noise sources in the circuit. Let's just keep these points in mind, and we will now go back to our discussion, which is I'll try to explain why do we need this RC filter and why should we connect the capacitor to supply. Okay, and does that make any difference if I had connected this capacitor to ground? So to understand that, we have to understand another very important property of a current mirror, which is the supply rejection property of a current mirror. So if you see this PMOS current mirror shown here, ideally the DC current at the output is simply N times Iref. Now let's say I add some noise to the supply. So you have VDD and I'm adding some noise Vn at the supply, and see how the circuit reacts to it. Now remember, the VGS is decided by this MOSFET. Now the current in this MOSFET is fixed, and that fixed current is given by Iref. Okay. Now because the current in that MOSFET is fixed, if I increase the VDD by Vn, the VGS is fixed, right? So because the current is fixed, the VGS is always fixed. Let's call it VGS Q as the quiescent VGS, which was corresponding to a reference current. Now I have just increased the source voltage by Vn. What will happen? Because your VGS is fixed, the gate voltage will also just increase by Vn. So if this node changes by Vn, what will happen here is that, so the source is changing by Vn, this node here also changes by the same amount, which is Vn. So therefore, if you see delta VGS, the change in VGS is 0. Now because the mirroring device's VGS is exactly the same as the reference device, the mirroring device will also see no change in the current. Right? The current in the mirroring device mainly depends upon VGS. I'm ignoring channel length modulation now. Okay, if you consider it, the analysis becomes a bit complicated, but for first order, I can easily see that the output current is independent of supply noise. So even independent of supply variations. So even if I change my supply by a small amount, the output current of a current mirror will not change. So that's the supply rejection property of a current mirror. So inherently, a current mirror structure gives you that benefit. Okay, and you can also see that from a small signal point of view. If you recall, a diode connected MOSFET can be represented as a resistor. It's a two-terminal device, right? So between source and drain and gate. So drain and gate are shorted. So it's a two-terminal device. This becomes, let's call it 1 by GM1, and this is small signal wise. This node is at Vn. And looking down, since it's an ideal current source, the output impedance is infinity. So it's open circuit. So this node also comes to Vn volts. So that's what I've shown here. The gate also comes to Vn in the small signal. So therefore, there is the change in the gate voltage. Okay, the change in the gate voltage is 0. The change in the gate to source voltage, delta VGS is 0. So therefore there will be no change in the drain current at the output. Okay, so this is what we call a supply rejection property of current mirrors. Again, this is a very basic rule, a basic principle that any current mirror designer should keep in mind. Okay, this is like a current mirror 101. It's a very basic principle to know. And I've just given you mathematical reasoning. Why is it so? Right? So a current mirror inherently rejects variations on the supply noise. Now we'll come back to the filtering. Why did we add the filtering, RC filtering in the current mirror? Now I said, if you look at the reference, let's assume the reference has a noise, IN. We said that that noise also gets multiplied by this factor, by, remember, n square. So the output, if your multiplication ratio is very large, then the noise gets amplified. So it's a current noise amplifier. It's like the noise of the reference is getting amplified by n square. And that's a huge problem. So how do we fix that? If you have a problem with the noise, the simplest solution is to add and cancel it out using filters. So now, if you recall the beginning of the lecture, I said the current mirror, the operation of a current mirror can be seen as a two-step process. The first step is whatever is applicable to DC is also applicable to noise. So the noise current IN flows through the diode connected MOS and it creates a noise voltage Vn. That then, if let's say there was no filter here, what would happen is that since this, let's call it VNR, this is the reference noise, is VNR, then the current at the output is simply given by GMN times VNR. And that can be shown to be simply N times IN. Okay, because GMN VNR is nothing but the noise voltage at this gate is simply, if you look at this equivalent representation, I'm just representing the diode connected device as a resistor of value 1 by GM. So the noise voltage here is simply given by IN1 upon GM1. So what I'll get here at the output is simply GMN times VNR, which is IN1 by GM1, and GMN by GM1 is N, right? So the VGS is same, only dimensions are different. So the ratio of the transconductance will simply be equal to the ratio of the device sizes. So it will be simply equal to N. GMN by GM1 will be N times IN, okay? Or IN1 or IN, whatever. So this is where the noise multiplication is happening. So what I need to do is that I know that I have access to the noise voltage at this gate terminal. So all I need to do to filter out that noise is just put a RC filter in between, in the path, in the signal path. So if I just add an RC filter here, then the gate voltage of the mirroring device, let's call it VGN, previously it was the same as the reference device, but now it's a filtered version of the reference device. By adding a filter, so this RC filter transfer function is shown here, so it has a pole at 1 by 2 pi RC. By adding a filter, I can easily show that the noise at the output, so that I'm plotting IN naught square will simply be N square IN1 square multiplied by the filtered transfer function. So that's actually filtered the whole square. So the noise gets filtered. I can choose the appropriate pole location based on my noise requirements. Okay, so typically you will either have a spot noise or an integrated noise spec. So if your noise at any given spot should be below a certain value, then you can choose your pole location in such a way that your noise requirement is met. Okay, let's not worry about the details there. The idea I'm trying to say is that by putting a resistor between the two gates, I'm accomplishing noise filtering. I'm able to filter out the reference noise. Okay, so that's why I'm adding the resistor between the two gates, because I have, at this node, I have the noise information available as a voltage. And a simple RC circuit is a voltage, a low pass voltage filter. Okay, so that's why we just added a low pass voltage filter. So I'm not doing a more exact analysis. You can do a more exact analysis and then show that the pole actually occurs at R plus 1 by Gm, but I'm making this assumption. R is much greater than the Gm of the reference device. So if I make that assumption, then this is perfectly fine. Okay, so that's it. I've just given a reasoning why we added an RC filter here. Now let's see what happens to the supply rejection property of a current mirror. So we said to filter out the noise, I added this RC filter, which is good, which is helping me in reducing this noise of the reference, because previously it was getting amplified by n square times. Now we are filtering it out. But let's see what happens to the supply rejection property. So to see the supply rejection property, first I'm going to assume that the reference has no noise. So this I can open circuit the reference here. Now we can represent this MOSFET for small signal purposes. We can represent it as a resistor of value 1 by Gm1. I'm just increasing the source node voltage by Vn volts. Now because the reference current source is ideal, the impedance of that current source is infinity. So therefore, if I wiggle this node, if I change the supply by Vn volts, then the gate or the drain terminal will also come to Vn volts. But now there is a small difference. So the change in VGS is 0 for this MOSFET. Delta VGS is 0. Previously, the VGN, the gate voltage of the mirroring device, was exactly equal to VG1 or VG here, or let me call VG1 here, was exactly equal to VG1. But now it's a filtered version of VG1. It's not the same as VG1. So therefore, what happens is that at very high frequencies, most of this VG1 doesn't even appear at VGN, which means it's getting filtered out. The capacitor will make this node AC ground. So if this node becomes AC ground, the circuit comes to something like this. You have this node reaching AC ground. So the change in VGS of the mirroring device is 0. The delta VGS in the reference device is 0. There is no change in the VGS there. But if you look at this device, the mirroring device, the source is at Vn volts and the gate is at ground. Okay, the gate is at ground, which means the supply noise entirely appears across the VGS. So therefore, the noise current here is going to be Gmn times Vn. Okay, and Gmn is very large because this device is carrying a lot of current. The W/L ratio is much higher. So therefore, you will directly see the impact of supply in the current that this current mirror is generating. So if I plot the noise current here, that noise current will contain, because this RC filter is filtering out the reference noise, it has almost killed it. But what I will be seeing as noise will be noise from the supply. The supply noise will be coming into this current as it is. In fact, it's getting multiplied by Gmn, which is it's getting converted by this transconductance factor. Gmn is a very large value. So you see a huge impact of the supply noise on the output current. So by adding this capacitor, even though I'm killing my noise of the reference current, I'm completely eliminating the supply rejection behavior at high frequencies for this current source. So current mirror is supposed to give me that benefit, but I'm completely taking it away. Now, how do we fix this? A quickest and the simplest fix is to make it supply effort. Let's say what happens when I connect the capacitor between these two nodes. Now first forget about supply noise. So which means your supply is ideal here. So because the supply is ideal, this node is AC ground, right? This node is AC ground now. So it's going to behave like a perfect RC filter for the noise. As far as noise is concerned, this noise will first create a small signal noise voltage, Vn, which gets filtered by the RC filter, right? And the supply is just a fixed voltage. So this node of the capacitor is always at AC ground. So it's going to give me the same filtering for the noise current. Okay, so as far as noise for the reference current is concerned, there is no change whether I connect the supply to ground or whether I connected the capacitor to gate and ground or gate and supply. But the difference comes when you add supply noise. What was happening when I added supply noise is that the gate of this node comes to Vn, because we saw that the current of this MOSFET is always fixed because you're forcing a constant current through it. So VGS, delta VGS is 0. So if I increase this node by Vn volts, gate will also increase by Vn volts. Now you have a situation that looks like this. The RC filter, the input of the RC is at Vn. Previously this was at ground. This node, because it was ground referred, was at ground, but now instead of ground, since it is connected to the supply, this node will also be at Vn. Now you can immediately see, if I have already analyzed this circuit in passive RC circuits. Let's say I connect R and C here. I am connecting both the terms to Vn. Let's say this is connected to Vn, this is connected to Vn, then the output here will also be Vn. Okay, you can immediately see if the impedance seen here is infinity, then it's just short circuited, right? You have just shorted these two nodes and you have one big impedance, and the node here is open. So whatever, so there is no current from input to this node, so this node will also be at Vn. Or you can just quickly apply superposition. Okay, treat this node voltage Vn as two independent but identical sources and find out VGN. So VGN will simply be given by Vn times H low pass, which will be Vn by 1 plus SRC. Remember, now VGN and Vn are Laplacian variables. It goes without saying. So I'm using small letters, but I hope that's clear. Plus, I can now assume noise present on the capacitor and the capacitor side and short circuit this. You will get Vn into SRC by 1 plus SRC. Add the two terms, you will simply get VGN equals Vn. So now if you see, the gate voltage here also comes to Vn. And therefore, the change in the current, the change in the output current will be 0. So previously I was seeing In without, if I ground referred the capacitor, I was seeing In was equal to GMN times Vn. But now, because both the gate and source are changing by the same value Vn, the change in the VGS for the current mirroring device is also 0. Therefore, the noise current at the output due to supply noise is 0. There is no change in the output current because of supply variations, or noise on the supply has no impact. So I have then recovered the supply rejection property of a current mirror. Okay, so that's it. That's the reasoning why I was showing the capacitor between the gate and the supply. So such capacitor arrangements are called supply referred capacitors. And there is another reason. It's much simpler. So generally, if you see, I've already said this in one of the previous lectures. How do you realize capacitors in integrated circuits? There are three ways. One is to use metal layers. So typically you will have two metal layers. You can draw two metal layers, and separated by some oxide thickness, you end up getting a parallel plate capacitor. This is typically realized using in any process. You will get some 4 to 5 or 6 to 7 layers of metals, and you can use some complex combination of those metals to realize capacitors, like parallel plate capacitors. So you have two conducting layers, and in sandwiched and in between is an oxide or an dielectric layer. Then you end up getting a parallel plate capacitor. Okay, so that can be realized by having two metal plates, which can be drawn using the layers of metals in a typical IC process. Or it can also be, capacitor can also be realized using MOSFETs. So what we do is, typically we just take an NMOS device and short circuit the bulk, drain and source. Then if you apply a gate voltage which is greater than VT, switching threshold, threshold voltage of the MOSFET, then we know that there will be a channel present here. So between drain and source there will be a channel, and then the channel will behave like a conducting plate. and the gate will be the other conducting plate, and the MOSFET will then behave like a parallel plate capacitor. The same holds true for PMOS devices as well. So if you can take a PMOS device and okay, so you can take a PMOS device, and I'm just showing a PMOS device, connect its drain and source and short it to bulk. So typically bulk is connected to the highest potential for a PMOS device. It happens to be VDD, and you get okay VGN to ground. So you realize a capacitor, which is this. So typically if you're realizing capacitors using PMOS devices, you will get what we call as the supply referred capacitors. If you're realizing capacitors using NMOS devices, you will typically realize it to ground. Okay, so because we normally connect bulk to ground, and since we are shorting gate, drain and source and bulk together, we would get a parallel plate capacitor, which will typically be ground referred. So there are three ways of realizing capacitors: NMOS, PMOS device, or you can use just two layers of metals. Okay, two plates of metals. So the first approach is typically called MIM capacitors, metal insulator metal or metal oxide metal. So often this is the literature. This is the nomenclature. We just call them MIM or MOM capacitors. And these are MOS capacitors. And in MOS also you have different flavors. But right now, let's not go there. What I'm trying to tell you is that you can realize it using metal or you can realize it using MOSFETs. Now, in current mirrors, because current mirror, for example, a PMOS current mirror, you already have this current mirror structure. What we normally do is that the resistor is realized using a linear region MOSFET, and the supply referred capacitor also happens to be a similar device as the current mirroring device. Okay, it's typically a PMOS device which is connected in this configuration. Okay, which is much easier. You already get it, and you just add this capacitor this way. Okay, and I have already discussed this previously as well. MOS capacitors will give you a higher cap density, which means in a given area, you will be able to realize a larger capacitor value using MOSFETs when you compare them to metal capacitors, purely metal capacitors. But MOSFETs, you should remember, they are nonlinear devices. The capacitance to voltage relationship is nonlinear. But when you are using it in DC circuits, those nonlinearity properties don't matter. Okay, so we don't really worry about the capacitor nonlinearities when we are putting them in biasing circuitry or circuits like this, for example, a current mirror. So I've explained it at a very basic level. Probably in a future lecture, I'll go a little bit deeper how to suppress this noise, how to choose the resistor and capacitor so that it's optimized for noise. Okay, so right now the goal of this lecture is to explain you this capacitor, why is it connected between gate and supply, and it's called supply referred arrangement. Why is it better over the ground referred arrangement? Now these are some very basic design rules. Now remember, you can't blindly apply every design rule for every analog design. Okay, so every design will have some custom rules. Sometimes it may turn out that ground referring may be better. Okay, so right now I'm not going through the details, but you may have some circuits where ground referring the capacitor might give you some benefits. But as a general rule, we tend to supply refer the capacitors if you are putting it in the filter in a PMOS current mirror as shown here. Okay, and I've given you what is the reasoning for that. Thank you.